thank you everyone for joining at the first meeting of Physics Education Research, uh, which is a division under Association of Nepali Physicists in America. So today I have invited, we have invited Dr. Andrew Duffy. Dr. Andrew Duffy has been teaching introductory physics at Boston University since 1996, very experienced. He has long had an interest in applying new technologies in the teaching and learning of physics. He was a key part of the development of interacting studio physics at Boston University. I am a big fan of studio physics. We started in 2018 as a pilot program, and after that, we never returned back to lecture, etc., which has been running in a dedicated classroom since 2013. He is currently the principal investigator of an NSF-funded education research project studying outcomes when simulations are used in labs and recitation activities. Today, Dr. Duffy will be presenting on using simulations to help students learn physics. So I would like to request everyone, just to avoid background noise, please keep muted. But when we go to Q&A session, of course, please unmute and ask question to Dr. Duffy. And also, I would like to quickly mention that ANPA has new student welcome program, so please keep tuned on that. You might be getting email. Our second program of PR division will be on October 26th, given by Dr. Justin Gambrell from Michigan State University on computational thinking. And also there will be Dr. Eric Dewey from Drexel University, who will also participate in discussion. With that, I would like to request Dr. Duffy with big thank. So I would like to request for presentation. Thank you so much.
Thank you very much, Rudra. So maybe I'll talk for 40 minutes or so and then leave plenty of time for questions at the end. And if there's no questions, I'm happy to show more simulations. So there's a link here to all my simulations. I put that in the chat earlier, and you can even find a link to this talk, which is really just a website, actually. And that was in the chat as well. So if you go to this first link, you actually come to this page here, and it just has a whole bunch of simulations listed. So it looks like there's 214 as of now. And right now it's got this one about the inner solar system, which is, I think, kind of interesting. So you can just center it on the sun if you want. And if you center it on the sun, and it just has the 4 inner planets, right? So it's got Mercury, Venus, Earth, and Mars. And if you center it on the sun, it's just, a few circles. And if you look at that, you go, how did it take us so long to figure this out? What was happening in the solar system? But if this is the version with the Earth as the center, and this is what things look like from our perspective, right? And so you can see that the paths followed by Mercury and Venus and Mars are fairly complicated, right? They do these funny little swirls, and they get very close to us sometimes, and then they're very far away at other times. And so when you see this version, I think you can understand why it took so long for humans to figure out what was happening in the solar system. So it's much easier when you see it from the sun's point of view. So that's why I like simulations. Is you can do things like this, and you can illustrate, what things look like over years or seconds or however long you need, depending on what you're looking at. So let's just scan down through these various categories. So these are pretty much listed in the order that you might go through this content in your classroom if you're teaching introductory physics. So motion in 1 dimension, 2-dimensional motion, projectile motion, some stuff about forces. They're not entirely mine. There's one here by Stephen Sayoun, which is really nice, which is about pushing a block. He's got a nice hand pushing a block along, so that's really nice. So every once in a while, you see some other ones that are not from me. Circular motion, and energy, gravitation, which is where this one is part of, rotation, harmonic motion, fluids, heat and thermodynamics, waves. And then we start getting to the more common material from the second semester. And so I've been teaching intro physics for a long time, like Ruder said, since 1996. So I've built up this collection which covers pretty much the whole course: circuits, magnetism, induction, a little bit of AC circuits. We don't do much AC circuits actually in our course anymore, so I don't have much on that. EM waves, a lot of optics. I really love optics, so I have some things on optics. I'll show you some of that later. That was reflection in mirrors, refraction in lenses has a whole bunch. Interference and diffraction, and then we're pretty much at the end there. And then there's some other links to other people's collections. Walter Fent has some lovely stuff. He has nice things. FET, of course, I'm not trying to compete with FET. FET is this massive team of people just making beautiful simulations. So I think we can all coexist here. I'm trying to do some very special purpose simulations, and FET does some really lovely general things. Their circuit simulator or their projectile motion simulation. Those are very nice. Okay, so that's what you get when you go to that website. So we talked about this. So there was one time I gave a talk at AAPT, the American Association of Physics Teachers, and you have to submit your abstract a year ahead of time. And so I submitted this abstract where I said 100 simulations in a year. That's what my talk was going to be on. And I set myself a goal of writing 100 simulations in a year, which was crazy, and I didn't make it. But I did do 85 that year. And so I did a word cloud of all the various things in the titles of these simulations. So you can see the kind of things that are emphasized: motion, interaction, gravitation. There's ranking tasks. So some of them have ranking tasks. A lot of them have graphs, So I think that's what's nice about these simulations is you can see a ball drop, but you also have a graph that goes with it, for instance. So, okay, so what am I going to try and talk about? So we already talked about the 200 simulations that are free for anybody to use. One of our recent projects is actually doing workshops at the American Association of Physics Teacher annual meetings and getting people to write simulate worksheets to go with our simulations. So I'll talk a little bit about that later. We use something called Top Hat in our course, and we have a whole ebook in there. The students don't buy a book anymore. They just pay a little bit extra on Top Hat to look at our ebook, and the simulations are included in that, so it's very interactive. We can focus a little bit on global warming and the simulations I have for that. And then if we have time, we can talk about our research project, which we call VIPER, Visualizations in Introductory Physics Education Research. And we're on our second 3-year grant from the NSF for that. And I am at Boston University down here. Okay, so let me show you another simulation. I'll show you a few examples here. So this one is kind of set up as kind of a puzzle, and if you do hit this button, you can get different scenarios. It just sort of randomly assigns charges to these 3 objects that are at the corners of an equilateral triangle. So let's try this one here. So blue is negative and red is positive. So we have 2 positive charges here and 1 negative charge. And you have to rank them based on the magnitudes of their charges. And all you have to go on are these arrows. And the arrows, of course, are showing you the net force on each of them because of the other 2. Okay, so there's no math involved. The students can't be plugging things into equations, really. So the idea is to say, okay, if you want to know how 2 compares to 3, you have to actually look at number 1. And it's like 3 and 2 are having a tug of war. So 2 is attracting 1, so it's got a force horizontally to the right towards 2. 3 is attracting 1, it's got a force directly towards 3. And you can see the net force is closer to the 3 arrow than the 2 arrow. And so 3 is winning the tug of war. And the distances are the same. And so you have to conclude that if 3 is winning the tug of war, it can only be because 3 is bigger than 2. Okay, so now we know that 3 is bigger than 2. So let's try another one. Let's look at 3 and we'll compare 1 and 2. And so here 1 is attracting 3 and 2 is repelling 3. And if those forces were equal, this net force area would be directly horizontal, but it isn't. It's closer to 1, so 1 is beating 2. So what did we decide? 3 is bigger than 2, and now we've got 1 bigger than 2. So 2 is definitely the least. And now we just have to look down here. This one's, I think, a little bit hard because this one is fairly close to the midpoint of the 1 force and the 3 force, but I think it's a little bit closer to 3. So I'm going to put my ranking as 3, 1, 2 and see if I'm right. Oh, I got it right. So that's nice. And if you got it wrong, you get another chance. And we can, if the students have a whole bunch of chances to figure this out. So I think it's a really nice conceptual setup, and they can get a lot of practice just with that conceptual thinking. Okay, here's another one about not charges. You could do it with charges as well, but these are masses interacting via gravity. Okay, so I'll hit the play button down here. And at the beginning, these are just assigned random velocities, and there's kind of assigned random masses. And you can watch as they interact with each other. And sometimes nothing really interesting happens, and other times lots of interesting things happen. And so you can just sort of watch the dance of these objects as they interact with each other. And so this guy 3 is kind of off on his own, but these two up here nicely interacting with one another. So you see some very interesting patterns happening here. Okay, and some of these you could just sort of watch for a while. It's just kind of interesting to watch. All right, what else we got? Thermo. So we get some thermodynamics going on. So we get some ideal gas particles in a box. And there's a particular state that we start off with a known pressure and volume and temperature. And now we can add or remove 400 joules of heat at various ways. We can do it at constant volume, constant pressure, constant temperature. Okay, so we can just try this and see what happens. So we added at constant volume. It's always 400 joules. And so you can see a constant volume process. Here's a constant pressure process. And it just keeps track of what the pressure and volume is doing, how that heat is split between the internal energy, the change in internal energy, and the work, things like that. This is always a monatomic ideal gas, so you get this, the change in internal energy here is 50% bigger than the work. That's typical for a monatomic ideal gas. Here's the constant temperature. You can remove heat if you want. If we just click this one, we'll go exactly back up the way we came, et cetera, et cetera. And you can see what the particles in the box are doing. The volume goes up, or they move around more energetically as the temperature goes up, things like that. Okay, what do we have here? So here now we get to charges. Oh, this one's nice because it's three-dimensional. And this three-dimensionality does not come from me. It comes from Wolfgang Bauer, who's at Michigan State University. And so he and I have run some workshops at APT in the past and on writing simulations. And he had this nice code, and he was kind enough to let me steal it to make some of my own simulations. Here's a nice optics scenario. And so this is the object here, this red arrow, so we can move that around. And this one's interesting because it doesn't directly show you where the image is, right? So this is the image, and you're allowed to put the image anywhere you want, right? So this is the wrong place for the image. But what happens if you do it here? And so the whole point of this simulation is to talk about the role that time plays. And time has a very interesting role in optics. So let's just watch as a wavefront travels away from the tip of the object. All those things hit the mirror at different times. Then you come back through here, and they pass through this image point at different times, okay? And so this is the wrong place to put the image. And you could try the image in all sorts of different locations. You'll find those different rays of light arrive at the image at different points. But here we can see the red and the green and the blue lines are actually really showing us where the image actually is. So we're going to put it there and see what happens there. Okay, so now this is where the image actually is. You can see that from the ray diagram. And we'll try it again. So I think it's pretty close to that. Okay, and you can see this is sort of a time delay for all these points. You see there's pretty much no time delay. So we'll hit that play button again. Again, they'll hit the mirror at different times. That doesn't matter, but the mirror kind of recenters the rays on this point. And then you see they all arrive at that image at the same time, and then they diverge away as if the light's diverging away from a real object. And so I think I just love looking at that because it really tells me something interesting about what time is doing, right? The image is formed at the point in space where all these rays of light take exactly the same amount of time to travel from the object to the mirror to the image. And it's the only point in space that that is true. Any other point in space, the times are not equal. So the image is not there. It's kind of a fascinating way to think about image formation, which we don't usually talk about. So I find that fascinating. Okay, last example before we talk about some other things. Yeah, here's a nice Newton's rings situation. And so we have a flat piece of glass and then a curved piece of glass on top of it. And we've shone light down from above. And we were looking at the two reflected rays. One ray has gone through the glass, come off the top surface of the air film that's in between those pieces of glass and come back. And the other ray has gone down through the film, bounced off the bottom surface of the film and come back. And you can see these rays interfering. Okay, and why do we get, oops, I need to move this slider here to get this thing in the middle. So what you see when the thing is in the middle, no matter what the color is, the color can be anything, you can adjust the color to be whatever you want in the visible spectrum, that is. No matter what the color is in the middle, we always get destructive interference, and you can see why. It's because you have a peak from one arriving where there's a trough from the other, and they just cancel each other out. Okay, but let's try a different point, right? So let's throw it over here, and here we'll put it at this place, which is constructive interference. You see a nice bright green line here, and you see a peak from one arriving at a peak from the other, so they are constructively interfering with each other. But if you change the wavelength to something else, that same spot might be, purely destructive interference or something in between, or you can get it back to constructive interference again, okay? So I think it's a nice way to demonstrate, what the effective wavelength is, and you can really see, why you're getting destructive interference. You've got peaks and troughs next to each other, so they cancel each other out. Okay, stop me at any time if anybody has questions, and if I'm just going to keep rambling on about things without looking at the meeting. So if somebody has a question, just yell at me, and I can stop. Great. Let me talk about these worksheets that we're working on recently. So our current status is we have 200 simulations or so. We have a few more than that, but it's about 200. And right now we have curricular materials to go with 50 of them. And that collection is gradually getting bigger as time goes by. Most of these are in-class worksheets, but we have labs, pre-lab activities, and discussion or recitation activities. And we're crowdsourcing this. So if you felt like you wanted to make a worksheet for one of our simulations, you are welcome to do that. And feel free to send it in, and I can post it on the site. And if it's hard to tell, which ones have worksheets. So going back to here, let me try and I know one for sure, which has one. I can find it in circuits. So this Ohm's Law one has a worksheet and what it says down here. So anytime you see here underneath the simulation, if there is a worksheet, then it'll say something like this. So there's a worksheet for this. And in fact, this was made by a Nepalese physicist, which is why I wanted to demonstrate that today. Okay, so I'll talk again a little bit more about this one in a minute. Okay, so we have put together, we've run a worksheet shop 4 different times at APT, and our first 3 consist of these roughly 10 people who wrote worksheets for us. And then we had one at the most recent meeting in July, which is where I ran into Rudra, and he invited me to give this session. And we had a ton of people. We had 15 people show up, all these people from Ben through to Brandon, and including Nishchal. And everybody embraced the workshop, which was all about, working and creating at least one worksheet to go with one of our simulations. So these folks added a whole bunch of worksheets into our collection, which was fantastic. Okay, so let's go back to this Ohm's Law 1, as we just talked about. And if you want to see the worksheet, I think you could click on this link and it would open up in this window. But the best thing to do actually is open it in a new tab. So we'll look at that worksheet in a second. And it's a fairly simple worksheet, but I think it's nice. And if you open it in a new tab, you have this functionality, make a copy for yourself. Okay, so you might go, well, I like this worksheet, but I want to change it a little bit. And what you do is go file, make a copy, and if you do that, you will then have a copy for yourself that you are free to edit, and you can give that version to your students if you would like. Okay, and any one of our worksheets, which are Google Docs like this, you can do that with. So that's how you make use of that. So what's happening in this one is, I like this, right? So you can actually see the conventional current. This conventional current is as if positive charges are flowing around the circuit. So there's what we typically look like, but it shows with students. You can just have the circuit diagram without that. That's kind of boring. And then I kind of like this version with the actual charge flow because you can see something very interesting happens at the battery, right? So if you look at the negative terminal, every once in a while, out of the middle of nowhere, just this positive charge and this electron show up. And you go, wow, that's like magic, isn't it? But no, it's actually chemistry, right? So there's a chemical reaction taking place here, which is doing this, which is liberating maybe an H plus ion and an electron. And the H pluses go through the battery and the electrons go off through the circuit and something interesting, heat your toast or whatever it is. And then they come back together here, and there's another chemical reaction that takes place there, which recycles those things and binds them together into some kind of waste product. So I think that's interesting to watch that. And a couple of questions on this nice worksheet is, what is the maximum current you can get out of this, and what's the minimum current, right? So right now we're at 3 amps. How could we increase the current? Well, we're almost at max now. We've got the maximum voltage. We know that if we take the resistance down as low as we can, we get the most current with the highest voltage. Okay, so 6 amps is the most. Then there's another question on there, which how do you get the least current? And so we have to do the opposite. Least voltage and most resistance will get the least current. And there's a big difference between the most and the least. You can see this is really running very, very slowly now. And that's really what current is, right? The rate of flow of charge. Okay, and so to answer questions like that, you have to have some basic understanding of circuits. But they're not questions which are directly answered by plugging and chugging into an equation. You really have to think about concepts. So I like that kind of thing. Okay. Yeah, so we have a studio classroom. Rudra was just talking about the classroom they have at WPI. So we have one that we've been running since 2013. Here's kind of a schematic view. There's 9 round tables of 9 students each. That's 81 students in our classroom. And so we now have 6 sections of 80 students running in there for our intro physics class every semester. And so we use up all of Monday, Wednesday, Friday for that. There's other courses that use up sometimes on Tuesday, Thursday, but our big use of this room is our algebra-based intro physics class. We do everything in this room. We do labs there. We do discussion times. There's a lot of times where On the walls, there's, oh, here you can see that. On the walls, there's a whole bunch of boards. So there's these display boards. We have 5 of those, but next to those, we have whiteboards. And there's the other side of the room, which you can't see, which is actually a whole bunch of frosted glass panels, and the students can write on those. So every single group of 3 in the classroom, there's 27 groups of 3, has a space on the wall that they are assigned. And so they're the best times in the room are when the students are working on worksheets, going to the boards, writing things out, and then you can look around the room and you go, okay, this group over here is totally getting it. I can see that just at a glance, but this group over here really needs my help. And so you go over and talk to them. And so there's 81 students, and we have 5 staff people in there. So there's usually someone like me, some professor of some sort, plus 2 graduate students, and then 2 undergraduate learning assistants. Okay, so here you can see, here's that frosted glass where people are working on worksheets. So we have 6 sections, mostly juniors, actually. It's an intro physics course, but most of them are juniors. They're mostly pre-med students, biology majors, life science majors in general. Over 60% female, and we really try and emphasize teamwork and active engagement. There are times when we are presenting slides in that room, but that's not what the room is for. The best times are when this is happening, as you can see in the picture, when people are working together on the boards. And you may or may not be familiar with learning assistants. And so these are students who have taken the course previously, and they come back to the course. They get paid to do this. They don't have to do any gradings. They just have the fun of interacting with the students. They just come back to the course to help the students learn. And so it's really fantastic to have those students in the classroom because, you know, a year ago they were actually students in the course. They really struggled with the material. So that is fresh in their mind about, you know, what do I have to think about when I try and answer this circuits problem? What are the issues I get stuck on? And they can really help direct the students. You know, their job is not to give the students the answer. Their job is simply to guide the students in the right direction. That's what they do. And they also helped us in our research when we had lab packets that we put together and simulations that we made to go with them. We'd sit the LAs down with the material. We'd have them go through, and we'd kind of do think aloud interviews as they went through them, and they helped us. They gave us lots of great feedback about how to improve our written material and how to improve the simulations as well. So that was fantastic. Okay, so there's an LA here in the middle working with these students on something that's happening in the classroom. This is probably a lab that's going on, so that's when we're using our computers there. Okay, we also have another way we use these simulations is in our interactive ebook on Top Hat, and I apologize for putting a sort of commercial advertisement in the talk. So our students pay $20 extra per semester, but that's the only fee they have. So if they've already bought Top Hat, which many of them have, then the only thing they have to buy for our course is $20 for this ebook. They don't buy a physical book. There's nothing else that they have to buy for the course. So what is it? It's an algebra-based intro physics ebook. It's got embedded simulations. It's got lots of questions. So they can, as they're going through the material, it asks them questions that they have to answer so they can assess whether they really understand it. And we give them a grade for 5% of the course grade, but almost all of them get that full 5 points because 50% of the ebook grade is based on participation, and we only graded at 50% of the possible total anyway. So the grade for that is just to get them to go through the ebook, encourage them to go through the ebook and do it. We actually have a ton of stuff on Top Hat. We do all our pre-labs there, many of which have simulations embedded in them. We do a lot of, all the lab reports actually come in on Top Hat and are mostly automatically graded. Our teaching fellows, teaching assistants have to grade small parts of those. Many of our labs actually are based on simulations or are kind of hybrid, and they go back and forth between simulations and hands-on material. And we also use Top Hat as our online homework system. It really wasn't designed for that. You could argue it's not a fantastic online homework platform, but the students don't have to pay an extra $35 a year or a semester for this other online homework system, whatever you happen to be using. So they get the whole thing for $20. So for us, it's been great. If anybody else is interested in adopting it, you can reach out to me. You're free to do it on Top Hat as well. But we've really liked that quite a lot. Okay, let me show you another simulation that's embedded in our Top Hat course. And I would say this one's a little bit flawed because you have to rank them from largest resistance to least resistance. But the way I set it up was there's 5 different things, and the answer for one of them is 1 ohm, and another one is 2 ohms, and another one's 3 ohms, another one's 4 ohms, another one's 5 ohms. But the 5 ohm one you have to put up here at the top where it says 1, and the 4 ohm you have to put on the 2, and the 2 ohm you have to put on the 4. So in some ways that's a little bit flawed. Okay, but the basic idea is this, right? So we go, okay, 5 and something gets us 8 in series. Okay, that one's easy. So we go, that one is 3, right? So we go, now you got to drag this across to 3, which is the middle of the 5, 4, 3, 2, 1 ranking. Okay, I don't know offhand what this is. 2 and something in parallel gets me 1.33. So I know it's bigger than 2, but I don't know quite what it is. So I'll come back to that one. Okay, 2 and 2 in parallel, that's 1, 1 and 4. Oh, because this one's 5. Okay, between X and Y, what's the resistance? That's 5, so I drag this one up to 5. Okay, 8 and 4, this one's 2, so 2 is the 4th highest, so that's there. What is this one? I'm going to do V squared over I. So my power is 16, my V squared is 16, so my V squared over R is what I meant to say. So power is V squared over R. I get 16 over something is 16, that has to be 1. So that is the least. Oh, I already put that somewhere else, though, did I? Oh, I know what happened. When I was dragging D somewhere, it mistakenly picked up E along the way. So I mistakenly put that one there. Okay, so I'm going to stick that there where we decided. So I'm going to claim that 2 and 4 in parallel gets us 1.33. Okay, so I don't know if I've got this right, but I think so. We'll see. Check your answer. It's going to say, oh, I did it, 5 out of 5. All right. And you can then, again, completely start over, right? So starting over gets you a different graph, gets you a different circuit, it gets you different problems up here, it gets you a different ranking. So all these go back to where they were. So the students get multiple chances to practice this. So they can do it over and over until they get really good at it. Okay, so that was that. Where are we now? 8 minutes after the hour, that's fine. Okay, so probably some of us are interested in global warming. I imagine that's pretty important for Nepal, actually. We have a lot of high mountains and snow and things like that. Okay, so I've got, this is a very, very simple one. Annual carbon dioxide emissions from US passenger vehicles. This is very US centered. My apologies for that, but the US actually is responsible for a big fraction of, significant fraction of the total global emissions. And so we can see the impact of things like, what if we doubled the gas mileage of the miles per gallon for a car? We, instead of 22, we go to 44, right? So you can say, hey, that's going to actually cut this big thing down by a factor of 2. And if we just reduced our miles driven, that would cut it down in a different way, right? We could get down to 1% of total global emissions from all the cars that are driven every year in America. But if you kind of do the opposite, you drive a lot more and your gas mileage is not that great, which most, the average American car is in the 20s somewhere. Then this goes up to, getting close to 3% of total global emissions just from Americans driving around in their vehicles every year. Okay, so that's just that. And you can look at your own personal vehicles. You can bring it down to yourself. And I think this is a fascinating statistic right here. There are 8.9 kilograms of CO2 associated with a gallon of gasoline. And if you think about that, you go, well, wait a second, a gallon of gas has a mass a lot less than 8.9 kilograms. So how can this be possible? But of course, what's happening is the carbon is coming from the gasoline, but the oxygen from the O2 is coming from the combustion process. So it's coming from the atmosphere. So in fact, the CO2 can have a mass that's larger than the mass of the gasoline itself. So there we go. Okay, so you can say, well, my car gets 36 miles a gallon. And of course, we're talking in America here, so we're still using crazy units like gallons and miles. Apologies to all the people who are used to thinking in metric, which is almost the entire rest of the world, of course. Okay, so there's that. Here's another one, which is not really a simulation. It's just a way to present the data. And so here you can look at energy consumption by source of, again, American energy. Okay, so let's do this sum graph, and I'll look at maybe fossil fuels and nuclear for the moment. Okay, so the black stuff at the bottom is coal, and so you can see that this is in units of quads. A quad is a quadrillion British thermal unit, quadrillion BTUs. That's approximately 10 to the 18 joules. Okay, so you can see that coal peaked around 2005, and then coal has come down. Let me do this individually for this, actually. So coal now is the black line, but you see as coal has declined, natural gas has gone up. So that's not great. That's still fossil fuels here, right? So, and petroleum in general is the red line. You can see nuclear was really nothing until 1970, and then it's pretty much flat for the last 25-ish years, 30 years. What about the renewables? Okay, so renewables are here, and the green one is the biomass. Hydro is pretty flat. Oh, the other thing to notice is that when you move from fossil fuels, this goes up to 48 quads, so you can see the units are completely different. Okay, so we're zoomed in when we get to the renewables. This is just 0 to 6, so we're way down on the scale. So be careful of that. And you can see that wind really took off in around 2000, 2005, and it's growing, which is nice. And solar was about 5 or 8 years later that it took off, but solar is growing as well. So that's kind of hopeful that at least these things have a very steep slope when you put everything together, all the types. You can see the renewables are still a pretty small slice of the pie, but before 2000, they didn't even show up on the graph. So at least now you can see them, right? You can see the contributions from the wind energy, all the wind turbines across the country, and all the solar panels. And I'm sure Rudra has noticed as well, when you drive around here in Massachusetts, every time you turn around, there's a new solar installation somewhere. Or you might see a new wind turbine here and there that you haven't seen before. This is a fascinating diagram here. So this is nothing to do with me. This comes from Lawrence Livermore National Lab, and they put one of these out every single year. And again, here's the 100 quads that US used in a year in 2022, and it goes, where is it coming from? But there's some fascinating things on here, right? So when you get to the end, you go, out of that 100 quads, actually 67, or basically 2/3 of that energy, is just completely wasted, right? Why is that? Because we're stuck with burning things. When you do that, you're limited by the second law of thermodynamics. Okay, so especially in transportation, where your useful energy is about 6 quads and your wasted is almost 22, so you've got an efficiency which is down in the 20 to 25% range. For electricity generation, at least it's like 13 to 24. It's like 1/3 and 2/3, right? But even in electricity generation, you're doing a lot of combustion, and so you have to reject, just because of the second law, you have to reject a lot of the energy. But literally 2/3 of the energy generated in the United States is just wasted, just goes off into the environment, adds to the global warming problem. And so if we can get more solar and wind, we'd be able to cut that number down and not be nearly as wasteful. So that's, I think, absolutely fascinating. We have a whole discussion packet on this that we give out in our classroom in the first semester. And again, I just opened it up in this window here. And if you do that and you try and do File, Make a Copy, you can't do it. So that's interesting. You actually have to, again, open this up in a new tab. And then if you want that packet to use in your own classroom, and you're free to use that if you'd like, when you get there, you will find that file, wait, maybe, it's File, Make a Copy is available to you. Okay, so if you find it doesn't, you have just open this, just open it in a tab, and you will be able to get that whole packet. And so I think it's a very nice packet to talk about. Yes, in Greenland, what would happen? It talks about energy use for a single person in the country. Where is it to the energy we take in daily in the food? It uses that historical energy graphing thing that I was showing you a couple minutes ago. And then it uses this crazy graph that I was just showing you with the energy flow in the students. So I think the students get a lot of insights into this by going through this worksheet. So feel free to make use of that if you'd like. Okay, what time are we at now? 11:17. Okay, so let me I will take like 2 more minutes just to maybe talk about our research a little bit. Okay, I'm working with 2 very good colleagues, Manraj Arawala, we are together at Boston University, and Emily Allen, who is now a physics teacher. She's actually runs the science program at Governor's Academy, which is a private school here in Massachusetts. We've been working together for quite a few years. We do things like this. We say this set of students are either going to get a simulation-based lab, and this set of students is going to get a hands-on lab. And then we kind of compare outcomes. And basically, we really haven't found any real difference between those groups. And so what we're doing now is we often find that a hybrid lab is kind of the best of both worlds. The students can see the ideal situation with a simulation, and then they go and look at a real life thing where there's complications, friction, things like that. And so they have to go back and forth between, well, this is the real life, momentum's clearly conserved in this particular case, and kinetic energy is not. Real life, momentum's not 100% conserved, but it's pretty close, right? So you can argue that you saw momentum conservation. And so we have a whole lab that's actually built around colliding carts. And so this is part of what the students interact with. And there are various things you can look at. You can look at momentum versus time, just a graph, or energy versus time, velocity versus time, position versus time. But I like this version, right? So here's momentum bar graphs, which means what? Let me just crank these numbers up so you can see some interesting things happening. Okay, and we can play this collision. Here we go. So it's a pretty, okay, these carts are equal mass. This guy's coming in pretty fast, 5 meters per second. This guy's moving left at 3 meters per second. So let's see what happens in this collision. It's an elastic collision, this one. Okay, so here's the outcome. And they just switch identities, actually, because they're equal masses. So that's kind of fascinating. And what's going on with these graphs? Okay, so the blue is before the collision. So here's momentum of cart 1 beforehand, here's momentum of cart 2 beforehand. The system, blue, is the sum of cart 1 and cart 2. Okay. The green is afterwards. So afterwards, cart 1 is moving left, so it's got a negative momentum. Cart 2 is moving right with a larger speed than cart 1 had, so its momentum is bigger. And again, green for cart 1 plus green for cart 2 gets us the system momentum. You can see the system momentum is conserved. That never will change, right? The before and after for the system should always be conserved here in our simulation. What are these orange lines, this is the momentum transferred to cart 1 by cart 2. And this line here is momentum transferred to cart 2 by cart 1. So those should always be equal and opposite, which is why the system doesn't have any. There's no net external force coming to the system, so that's always 0. And we can reset this, and we can run it again with a different elasticity. So this kind of tells me, it helps me understand what elasticity is, right? So just pay attention to the size of these orange lines, the transfer to, the impulse. This is the impulse, right? Okay, so I'm going to go to the other extreme. I'll go all the way down to a completely inelastic collision. And we haven't changed anything about the system beforehand. So the blue lines are the same. The green lines are different individually, but the system green is the same because momentum's conserved. And these are much smaller than they were before. And so elasticity is about how much momentum is actually being transferred. Don't need that. Between these carts. Okay, so let's see this one. So it's the same initial conditions, but a completely different outcome because we changed the elasticity parameter. Okay, so the students have to make sense of something like this. And I just love this set of graphs because there's so much kind of self-consistency built in, right? This blue plus that blue has to always add up to this blue. This green plus this green has to add up to this green. These two system lines always have to be the same as each other. These two oranges have to be equal and opposite to each other. This green is the sum of that blue and this orange. Same with this, right? So there's just so many ways you can connect the different contributions to the momentum. Okay, so the last thing I'm going to say is just what is here. We have labs for these things. If you want the whole set of labs we have various things. We've got an energy simulation here, which is just about this block sliding down and looking at energy versus position and energy versus time. We have a discussion activity for that you have access to. We have a rotational dynamics simulation. This one, I like the one that's on the screen because you can see energy versus time is quadratic, energy versus position is linear. So we like doing that. Here's a rotation one, which is about a block and a pulley. Oh my goodness, this one is crazy. There's so much going on with this. We can talk about that. Let me just stop for at least a few minutes and see if there are any questions.
Okay, thank you so much, Dr. Duffy, for this excellent presentation. So much resources here, like so many kinds of resources. Thank you so much for sharing with us, and very nice presentation. So if there is any question from the audience, please either put on the chat box. I can read the question. Like we have about 7 minutes to respect your time. It is about 1 hour long program. So 11:30 is 7 minutes away from us, so that is US Eastern time. So there is a question, one question I believe Dr. Ramesh Dungana has asked: do you provide the link to Google document that contains all worksheet? I think it is the best way to know which simulation have worksheet.
Yeah, I could do that. Let me stop sharing for a second, and I should be able to find that and put that in the chat because I do have such a document.
Okay, great.
So sure.
Yeah, thank you. So in the meantime, if there is any question from participants, please either unmute and ask to the presenter or put in the chat box. I will be happy to read your question. So while we are waiting for question, like one simulation like the Kepler's laws, like related to gravity. So that is basically like the theory behind it is a Newtonian gravity, right? Not the space-time thing, not Einsteinian gravity, right?
Yes, it's very Newtonian. You're right, absolutely right.
Okay, thank you.
Okay, let me see if I can put this link here.
Yeah, I have a quick question. Very excellent talk. So how do you introduce the retrograde motion in the class when you have to talk about the retrograde motion, talking the astronomy based on the Earth-based system, like you have shown in the first simulation? You have to
Yeah,
introduce, but that's sometimes pretty confusing to tell the student.
yeah. So let's talk about that. Let me share that screen again, if I can do that.
Okay, in the meantime, Dr. Duffy has shared the Google Doc of the all simulation, I believe, all worksheets. So that is in the chat box. Please feel free to click on that. Thank you.
Yeah, and that is a whole spreadsheet. It's not editable, but you can look at it. You can see which ones have simulations. Okay, so where was my, oh, I guess I took that away. No. Oh, here it is. Yeah. Okay, so let's go back and look at this one here. So I'll go back to the, well, here's the sun point of view, right? So this is pretty boring. This little strip at the bottom is showing that if you were on the sun, somehow standing on the sun and looking at a point in the sky, this is what you would see. You would see, Venus going by pretty quickly, all in the same direction, right? So this is the sun's point of view. If you go from the Earth's point of view, you'll always see the sun going across the sky in the same direction. And these little guys are Mars is red, and Venus is green, and Mercury is purple. Okay, so now we're seeing Mercury go the other way. So there's that retrograde motion. And of course, what's really happening is Mercury is just continuing to go along in its circular path around the sun, and so is the Earth. But from the Earth's point of view, there are times, you can see one happening here, where when you look up in the sky, it just appears to us that Mercury is going the opposite direction. And this at the bottom kind of is trying to demonstrate that. We're just about to see Venus. Venus is getting pretty close. It's going to do the same kind of thing. Okay. This strip on the bottom, the planets are shown kind of actual size as you pretty much see them in the sky. The sun is shrunk down by a factor of 60. Otherwise, it would dominate this thing. Okay, so there you can again see Venus kind of going the wrong way in the sky. And so there's that retrograde motion. So really it's still going around the sun just like we are, but it's moving faster than us. There are times when it just appears to us like it's going backwards in the sky the wrong way. So this is how I talk about it. I use this little strip at the bottom, which is kind of showing you what happens when you kind of look up in the sky. You get the full 360-degree view. And most of the time, these planets are seen going right to left on this strip, but there are occasional times when they go the other way. And they're consistent with this funny little spin that's happening. You can see one happening right here for Mercury now. So, and you can see Mercury going the wrong way in the sky. Okay, so that's how I do that.
Thank you so much. There is another question in the chat box, I believe. Thank you for the wonderful resources sharing to us. This is from Ramkrishna Adhikari. I believe he's in Nepal now. I want to know what is your suggestive mode for the use of simulation containing worksheets taking one simulation in example.
Yeah, I mean, we saw this this Ohm's law one, right? So, and we do this all the time in our studio classroom. We stop talking and we say, all right, here's a worksheet for you guys to work on together. Here's a simulation that goes with it. And so we'll give the students time in class for them to bring up the simulation, try and think about these questions, work together. And so instead of us telling them how everything works, they're actually figuring it out for themselves. And there's some guidance here. And of course, we probably would have introduced some things about Ohm's law before we got to this worksheet. But that's how most of the time we use them in class. So with the Google Docs, they're designed for the students to use working together in small groups along with the simulation.
Thank you so much. Just a quick question, just a follow-up question. Will these be graded by the TAs, PLAs, or these are not graded?
Typically what we do is we pick out just a couple of questions from our worksheets and we put them into Top Hat, and the students answer them on Top Hat, and then they get automatically graded. So we don't get them to hand in the entire worksheet. We just do a very quick assessment.
Great. So for 81 students, you said one instructor, yourself or Manar or somebody, and 2 graduate teaching assistants. And how many learning assistants?
2.
2. Okay, fantastic.
Yep. There's a total of 5 people in the room for 81 students.
Okay, great. Thank you. So here is a question from Dr. Ramesh Lungan again. Has anyone tried to embed these on Canvas so that they can run inside the Canvas?
That I do not know. I mean, one thing I can tell you is that you have access to the whole, you can get, for instance, for each one, you can actually get the code. Okay, so if I bring one of these up, here, let me do it from here. So I'm going to open this just random one in a new tab. Okay, so if I right click on this, I can view the page source. And it'll show you the entire HTML5 code, which you can copy and paste into an editor. And so you can have that, right? So you can do whatever you like with it. You could upload that to wherever you want as a web page, and it should run. Now, the other way to do it is just embed links into Canvas. That should work as well. That will take you to my website, and they should run from there. But if you want to actually do them offline somehow, you can actually get all the code and put it wherever you want. That's totally fine.
Great. There's one more question. Thank you for your wonderful presentation. This is from Siva Zisi. I believe Siva is in a very far western part of Nepal. Thank you for coming, by the way. Please provide the information how to make this type of, how can we make this kind of worksheet? So that means based on your simulation, like, so Siva wants to create worksheets, like, so anything to say? Yeah.
Yep. So this is what I do, and this is what I encourage anybody who wants to do it to do. So don't start from scratch. I always start something like this. And of course, starting from scratch is not hard either. But what I would do here is I would do file, make a copy on just a random sheet. And then I get my own copy. And I can edit that. And I can now change this to be whatever I want, right? It doesn't have to be on Ohm's law anymore. It could be on some projectile motion simulation. So I'll change the title, I'll change questions, I'll change the link, and then you get a new worksheet to go with a different simulation. So I think it's super easy to do. Google Docs just make it very easy to edit. So the process that I use myself.
Thank you. Yeah, that will save like time and also energy. Yeah, thank you.
Right.
Thank you so much. Probably at this point of time, we are like about 1 hour. So let's thank Dr. Duffy for this excellent presentation and showing a lot of resources. These are very, very useful resources. Like many of our faculty at WPI are using, myself and other faculty members are using these resources. So anybody can use these resources for free, right? I believe that's right.
Yep.
Okay.
Absolutely free. Yep.
Thank you. Thank you so much, Dr. Duffy. And in case you would like to travel to Nepal sometime in future, like probably we'll organize another workshop in Nepal in person.